Alright, for the last half of the course we're going to talk about logic programming. So we're going to do this in 3 steps. We're going to provide 3 languages we're going to provide. One is called propositional logic programs. And this is sort of like the propositional logic but converted into a simpler form of logic programs. Then we look for a data log which intuitively allow for logical variables in clauses and queries as far as the logic is concerned, but it's really an extent. The other way to view it is an extension of the relational database operators. Okay, and the third one is prolog, which is data log plus it allows for function symbols, and that makes it into a rich, powerful programming language. Okay, so first of all, we're going to start off with propositional logic programs. So what we're going to do is here's a few definitions for us. So an atom is just to the form, P. We're just going to use as a predicate symbol. That's a word that can contain letters, digits, and underscore. So that's the words we can do here, and it starts with lowercase letter. So we're going to write theirs in that form. So a body is either an atom defined above, or it's this operator with a comma between it. So it's B1, B2, and these parentheses are optional. And this comma is going to mean and. So this is going to mean that B1 is true and B2 is true. An atom is going to be something that's true or false. And then we're going to have a definite clause is either an atomic clause, just an atom, or a rule H if B, where H is the head, is an atom, and B is the body. And that's going to mean if. So it's going to mean H is true if B is true, or just stating in the atomic clause, just saying that is true. So an atomic clause is treated as a rule with an empty body. And all these definite clauses end with a dot. So you can tell when they end because they have a period at the end. Alright. So a logic program is just a set of these definite clauses. And a query is a body that's asked in the prolog prompt. So if you think back to Haskell, so the colon minus is like the equals in Haskell. Alright, so it's just the equals in Haskell. It's just that now in the right hand side of this we can have elements separated by commas. Okay, so instead of having nested expressions, we're going to have atoms separated by commas. So we can extend that to data log is of the form P of T1 down to Tn, or just P. So before we just had P, but now we can extend it to have arguments in here. P is a predicate symbol. Again, it's going to start with a lowercase letter. And this word can contain letters, digits, and the underscore. And each of these arguments, these TIs here, is either a term, is either a constant, is called a term. So each of these arguments here is called a term. A term is either a constant, so a number, like 3 is a constant, or a word starting with a lowercase letter. And a logical variable is a word starting with an uppercase letter or starting with an underscore. Okay, so in here, the variables here can start with an uppercase, but also underscore can be used in these. Alright, that's the language. So in a clause, a variable means for all. So here's a rule that says X is a grandmother of Z if X is a mother of Y and Y is a parent of Z. So there's a definition of grandmother, right? It's the mother of a parent. So X, Y, and Z here are variables, and it's true for all. So if there's any X and any Y and any Z, such that mother is a So that X is a mother of Y and Y is a parent of Z, then X is a parent of Z. Okay, and that happens for all values of X, Y, and Z. So if you find this is true, the right-hand side, then the left-hand side must be true. And the query, the variable is asking whether there exists an instance. So this one here, does there exist a person G who is the grandmother of Xavier? Now here Xavier is a constant. It's going to denote some particular individual. And G is going to be a variable here. It's asked, does there exist a G? Is there some G such that G is the grandmother of Xavier? Okay, that's a syntax for us. So here's an example we're going to give. We're going to call this the electrical environment. So in here we have an outside power, and it goes into circuit breakers. And then in circuit breakers, these red things here are wires. And the wires go into switches, and the switch goes either up or down. And if it's down and there's power in that, then there's going to be power in W2. Switch S2 then switches between wires W1, W2. If it's up, it's connected to W1. If it's down, it was connected to W2. There's another wire here that goes to light L1 that could be lit or not. Right, so if you move S2 down, it's going to turn the light on. Or if you move S1 up. So this, by the way, is how light switches that when you have a light in a hallway that has a switch at both ends. This is how it works. Okay, so if you switch it up, it connects it to one wire. If you switch it down, it connects to another wire. And now we have, this some again. So S3 is a switch when it's up, and there's power in the outside. From the outside comes through circuit breaker 1, comes through W1. If it's up, it goes to W1, and L2 is lit. Okay, so that's an ongoing example we're going to use. So here are some facts about the world. So L1 is a light. So we're allowed to use underscore in here. So here's a statement that says L1 is a light. S1, switch S1 is down. So this is an atom we're going to use. S1 is down. So we're going to write down S1 and up S2. And that's supposed to be correspond here. So down S1 is because S1 is down, and up S2 because S1 is up. Okay, so we're going to state facts about the world. And here's a rule. L1 is lit if W0 is live and L1 is okay. So let's go back to here. So L1 is lit, right? If W1 is live, if W0 is live and L1 is okay. Okay. Whoops. W0 is live if W1 is live and the switch is up, S2 is up, and live W0 is true if W2 is live and S2 is down. So let's look at that. So this one here is live if S2 is up and W1 is live, and W0 is live if S2 is down and W2 is live. So live means there's electricity flowing through it. Okay, so that's the sort of things we can write in here. Okay, there's a complete list of it there, and you can find it in elect prop. So now we're going to talk about what does all this mean. So here's a human's view of semantics. We're going to start with a task domain, like that electrical domain. We're going to choose atoms in the computer to denote propositions. And so these atoms have a meaning. So in our example before, these might have a meaning. The human nose is going to have some particular meaning to the human being. That W1 is live. You get electrocuted if you put your finger on it. Up S1 is a proposition that's true. We have a meaning to it, namely that switch S1 is up. Okay, so we can choose atoms, and these atoms have meanings to me as the designer. And I'm going to tell the system knowledge about the domain. I'm going to ask the system questions, and the system's going to give answers. And I'm going to interpret the answers with the meaning associated with the atom. So now I ask, is light L1 lit? Is lit L1 true? I know what that means, and so it's going to ask me a question about the domain. So I'm going to think about the domain. Here's the switch again, so I can ask, is lit L1? And it might say no. If I change the domain so that S2 is down, then it might say yes. If I ask, is lit L1, lit L true, it's going to say yes, because it's going to follow from its doing it. Okay, so here's an example. So in the user's mind, our light L1 is broken, has this atom here, this is an atom, has a meaning. Light L1 is broken. SW switch 1 is up, has a meaning. SW1 is up, has a meaning that switch 1 is up. Similar for switch 2. Power as a proposition means there's a power coming into the building. And they might have an atom like light L1, unlit light 1 has a meaning that light 1 isn't lit. In the computer doesn't know what these meanings is, but you're going to tell it facts. So in the computer it knows that you tell it that SW1 is up, so it knows that. And you're going to tell it that light 1 is broken if switch 1 is up, switch 2 is up, there's power in the building, but the light's not on, so light must be broken. So you're going to tell it there's power in the building if the other light is lit, so we know whether it's power in the building. The computer can then conclude that light 1 must be broken. Now what happens here is the computer doesn't know the meaning of these symbols. So in the user's mind, all of these symbols have meaning. The computer doesn't know what they mean. However, the user can interpret the symbols using their meaning. Okay. All right, so how do we define this? So let's write this down. So interpretation assigns a truth value to each atom. And you would have seen this in your first year computer science courses. So the truth of a compound proposition is derived from this truth table. Remember, this is AND. So P and Q is true only if P and Q is true, otherwise it's false. This is read as if, so P if Q is false, if Q is true and P is false, otherwise P if Q is true. Okay, so that's the meaning of these, the semantics of what these mean as logical operators. So a body is true if B1 is true and B2 is true. So that's what it's going to mean. A rule H if B is false in some interpretation if B is true in I and H is false in I. So it's false if H is false and B is true, because you found the counter. You've said that H is true if B, but it's not true because B was true and H is not true. And the rule is going to be true otherwise. So that's what that's going to mean. Okay. So the knowledge base is true if in some interpretation, if and only if every knowledge base is true in the interpretation. Notice we're careful here, we've got to be careful, it's true in a particular interpretation. So there got to be other interpretations in which it's false. Right? So the interpretation is what assigns a truth value to each atom. So the interpretation assigns a truth value to each atom, and then we can use this to work out what's true. Right. So now a model of a set of clauses is an interpretation in which all the clauses are true. So that's a model. It's just an interpretation in which all the clauses are true. And a knowledge base is a set of clauses, and G is a set of conjunction of atoms. Then G is a logical consequence. We're going to use this funny symbol, this double turnstile, this KB logically implies G, if G is true in every model of the knowledge base. Okay, so this means that G is true in every model of the knowledge base. So not a model is an interpretation in which all the clauses are true, and so this means that G is true in every model of the knowledge base. So there's no model of the knowledge base, there's no set of meanings of there's no set of assignments of values to the knowledge base where all of the clauses are true in that knowledge base and G is not true. Okay, so knowledge base KB implies G logically, G is a logical consequence, or knowledge base logically entails G if there's no interpretation of the knowledge base, no interpretation in which the knowledge base is true and G is false. Okay, now prologue says yes to a query if the query is a logical consequence, otherwise it's going to say no. So we're going to ask about whether logical consequence. And SWI prologue, by the way, uses true and false, but I think that's sort of confusing. So I'm going to talk a bit about yes and no. So it means logical consequence. So yes means it is a logical consequence, and no means it's not a logical consequence. All right, we're going to give lots more examples in class. Thanks for listening.